Hey there, and welcome. In chemistry, we talk a lot about things being insoluble. But what does that really mean? It turns out it's not quite the open and shut case you might think. Today, we're going to pull back the curtain on this idea and really get to know the solubility product constant, or Ksp.
I'm sure you remember staring at a chart just like this one in chemistry class, right? Trying to memorize all those rules. It gives you a pretty black and white picture. Some things dissolve, some things don't. And you know what? It's a fantastic place to start when you're predicting reactions.
But what if that clean line between soluble and insoluble is, well, a little bit of a simplification? What if it's actually more of a sliding scale? And here is the big reveal. In the real world, pretty much nothing is 100% totally insoluble. Nope, even the compounds we label as insoluble, the ones that look like they're just sitting at the bottom of the beaker, will dissolve just a tiny but measurable amount in water.
So when you have a saturated solution, it's not just sitting there doing nothing. It's actually buzzing with activity. At the molecular level, you've got the solid constantly dissolving into ions. And at the exact same time, those ions are crashing back together to reform the solid. It's this beautiful, perfectly balanced dance called a dynamic equilibrium.
Okay, so if these things dissolve just a tiny bit, how on earth do we measure that? How do we put a number on that equilibrium? Well, that is where our star for today's show comes in, the Ksp.
So the official definition is that Ksp is the equilibrium constant specifically for a solid dissolving. But think of it this way. It's just a number that tells you exactly how soluble one of these slightly soluble compounds really is at a certain temperature.
And the best part is, interpreting it is super straightforward. A bigger Ksp means it's more soluble. A really tiny Ksp, like for something like silver bromide, tells you that it is way less soluble. Simple as that. Bigger number, more dissolving. Smaller number, less dissolving.
All right, so how do we write the expression for Ksp? It's a simple three-step recipe. First, you write out the balanced equation for the solid breaking apart into its ions. Next, you write the expression by multiplying the concentrations of the products, the ions. And here's the key. Don't forget that the solid itself doesn't show up in the expression. Finally, you take the coefficient for each ion from your balanced equation, and that becomes its exponent. That's it. Okay, theory is one thing, but let's actually put this to work. We can take a known Ksp value and use it to calculate exactly how much of a compound can dissolve in water. We call that its molar solubility. Let's take calcium fluoride, or CaF2. When one little unit of this stuff dissolves, it breaks apart into one calcium ion and, pay attention here, two fluoride ions. That 1-to-2 ratio is going to be super important. So, following the rules we just talked about, our Ksp expression is the concentration of calcium ions times the concentration of fluoride ions squared. See, that squared comes directly from that coefficient of 2 we just pointed out in the balanced equation. Now for the fun part, a little algebra. Let's define the molar solubility, the amount that dissolves, as X. Because of that 1-to-2 ratio, if X moles of the solid dissolve, we're going to get X moles of calcium ions, and we're going to get 2X moles of fluoride ions. It all goes back to that ratio. Okay, now we just have to plug these X values back into our Ksp expression. So we get Ksp equals X times the quantity 2X squared. Remember to square the whole 2X term. That gives us 4X squared, and when we multiply by the other X, we get our final relationship. Ksp equals 4X cubed. So we can look up the Ksp value for calcium fluoride, plug it into our equation, and solve for X. And what do we get? We find that its molar solubility is about 2.1 times 10 to the negative 4 moles per liter. See? A super small number, but it's not zero. It's a real, measurable amount. All right, calculating solubility is pretty cool, but one of the most powerful things we can do with Ksp is predict whether or not a solid, what we call a precipitate, is actually going to form when we mix two different solutions together. I mean, this is a classic chemistry scenario, isn't it? You've got two perfectly clear liquids, you pour them into the same beaker, and what happens? Does it stay clear, or does a solid suddenly appear out of nowhere? Well, Ksp gives us the superpower to know the answer before we even mix them. The way we do this is by calculating something called the reaction quotient, Q. It looks just like the Ksp expression, but we use the initial concentrations, right when we mix them.
Then we just compare Q to Ksp. If Q is smaller than Ksp, we're good, no precipitate. If Q is bigger than Ksp, uh-oh, a solid has to form until things get back into balance. And this is what that looks like in real life. When your initial mix of ions is just too high, when your Q is greater than your Ksp, the solution is what we call supersaturated. It's unstable, and the only way for the system to fix itself is to kick those extra ions out of the solution and form a solid. You're literally watching equilibrium happen right before your eyes. Okay, you ready to level up? Let's talk about a really slick application of all this. What happens if we try to dissolve one of our salts, not in pure water, but in a solution that already contains one of its ions? This is called the common ion effect, and really it's just a classic case of Le Chatelier's principle. Think about it. If you add more of one of the products, this common ion, you're putting a stress on the equilibrium. And how does the system relieve that stress? It shifts to the left, using up those extra ions and forcing more solid to precipitate out of the solution. Let's look at a real example to see how dramatic this can be. We're going to calculate the solubility of barium sulfate. First, we'll do it in pure water. Then we'll calculate it again, but this time in a solution that already has some barium ions floating around in it. The difference is absolutely incredible. Check this out. In pure water, the solubility of barium sulfate is about 10 to the minus 5 molar. But when we try to dissolve it in that solution with the common barium ion, the solubility plummets to 10 to the minus 8. That's not just a small tweak. We just made an insoluble compound nearly 1,000 times less soluble just by changing what it's dissolved in. So I think the big takeaway here is that Ksp isn't just some random number in a textbook. It's a genuinely powerful and practical tool that chemists use all the time to understand, to predict, and even to control what's happening inside a solution.
And that leaves us with a final question to chew on. If different compounds have wildly different Ksp values, and if you can manipulate their solubility using the common ion effect, how could you use that knowledge to, say, pull just one specific metal ion out of a complex mixture, leaving all the others behind? That right there, that's the power of understanding Ksp.